Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join in my channel as a member and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held in the month of March 2025. It is a rescheduled examination meant for Assam state. In this video, we discuss the solution of a problem from the section Linear Algebra, and it is related to the concepts of the spanning sets and linearly independent sets. Right. This question is placed in part C, which is a multiple select question. There may be more than one answer and it carries 4.75 marks. The question ID is 706551. Further, this question is suitable for all these examinations. Right. The given question is, for each n greater than 1, let V denote the C vector space of all n by n complex matrices and A belongs to V. Which of the following are necessarily true? We are given 4 options. Option 1, the set consisting of I, A, etc. A power n is linearly independent, but the set consisting of I, A, etc. A to the power of n square is not linearly independent. Option 2, if A is a singular matrix, then the set consisting of I, A, etc. A power k spans a k plus 1 dimensional subspace of V for all k less than or equal to rank of A. Option 3, the set consisting of I, A, etc. A power n and the set consisting of I, A, etc. A power n square both span the same subspace of V. Option 4, the set consisting of I, A, etc. A power n is linearly dependent. It's a very simple and straightforward question, and this uses the definition of linearly independent set, linearly dependent set, the spanning sets, and so on and so forth. Right. Let's now get into the solution. We have the C vector space. We mean a vector space over C. That vector space is denoted by V is equal to Mn C, the set of all the vector space of all n by n matrices with the entries coming from C, where n is greater than 1 and A is an element of V. A is a matrix from V. Clearly, what will be the dimension of V over C? It is an n by n matrix. It is n square. Yes, we know it. Now we take the option 1. The set consisting of I, A, etc. A power n is linearly independent, but the set consisting of I, A, etc. A power n square is not linearly independent. Option 4, the set consisting of I, A, etc. a power n is linearly dependent. Right. Let the characteristic equation of the matrix A be chi A of x is, let us say, C0 plus C1x plus etc. plus Cn minus 1x to the power of n minus 1 plus x to the power of n. Right? The leading coefficient of x to the power of n will be 1. Right. Right. By Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. That means chi A of A is equal to 0. That means to say C0I plus C1A plus etc. plus Cn minus 1a to the power of n minus 1 plus a power n. Then a power n can be written as is equal to minus C0I minus C1a plus etc. plus Cn minus 1 into a to the power of n minus 1. That means a power n is a linear combination of I, a, etc. etc. a power n minus 1. Therefore, the set consisting of I, a, etc. a power n is linearly dependent over C because one of the matrix, this matrix A power n, is written as a linear combination of the preceding elements. Right. Linearly dependent over C. So, option 4 is true. Agreed. Let's see what happens to this one. With this much of information, we can throw away the option 1 also. Option 1 is not true. But anyway, having come this far, let us see whether this set, that is the set consisting of I, a, etc. a power n square, is it linearly independent or dependent? So, the set consisting of I, a, etc. a to the power of n square is linearly dependent. Why? Because these are n square plus 1 elements in V whose dimension is n square. And you know, every set consisting of n plus 1 elements in an n-dimensional vector space is always linearly dependent. That's the result, what we are using. Therefore, I, a to the power of n square is linearly dependent, is not linearly, right, this is not linearly independent. So, it is linearly dependent, but the beginning, this one, the set I, a power n is linearly independent is given, but it is given, but we have proved that it is dependent. Therefore, option 1 is not true. Agreed. So, let's go to the option 3, the sets consisting of I, a, etc. a power n, and the set consisting of I, a, etc. a power n square, both span the same subspace V. Subspace of V, not subspace V. Subspace of V. Of is not written here. By Cayley-Hamilton theorem, a power n is a linear combination of I, a, etc. a to the power of n minus 1. From this, it follows what will be a to the power of n plus 1. A to the power of n plus 1 is a linear combination of I, a square, a power n. But a power n is a linear combination of I, a, etc. a to the power of n minus 1. Therefore, a power n minus 1, a power n plus 1, a power n plus 1, and a power n plus 2, so on and so forth, a power n square, they are all linear combination of matrices I, a to the power of n minus 1. So, So let us take the linear span. The linear span of I, A, etc. e to the power of n square is equal to the linear span of I, A, etc. e to the power of n minus 1, comma, a power n plus 1, etc. a power n square. These red ones, a power n plus 1, etc. a power n square are the linear combination of I, a to the power of n minus 1. Therefore, it's the linear span of I, a to the power of n minus 1. Agreed. Let us take the first set. The linear span of first set I, a to the power of n minus 1 a power n, in which a power n is a linear combination of I, a, etc. a to the power of n minus 1. Therefore, it is a linear span of I, a, etc. a to the power of n minus 1. So, both of them are the linear span of the same subspace, that is I, a, etc. e to the power of n minus 1. Therefore, they are equal. Therefore, the linear span of I, a, etc. e to the power of n square is equal to the linear span of I, a, etc. a power n. Therefore, these two subsets span the same subspace. Both of them span the same subspace. So, that is the sets I, a, etc. a power n and I, a, etc. a to the power of n square both span the same subspace of V. Of V is missing. Right. So, the option 3 is true. So far option 4 is true and option 3 is true. Let's move to the next slide. Okay. We go for option 2. If A is a singular matrix, then the set consisting of I, A, etc. a power k spans k plus 1 dimensional subspace of V for all k less than or equal to rank of A. Is it true? It is not true. So, we will give you a counter example. Let n is equal to 3. Then V is M3 over C. Right. Let us take the matrix A to be 1, 0, 0, 0, 1, 0, third row 0, 0, 0. Clearly, it is singular. Why? Because the third row is a 0 row. Therefore, its determinant will be 0. Therefore, it is singular. And the rank of A is 2. It's very clear. It's in the row reduced echelon form. And we have 2 non-zero rows in this. Therefore, the rank of A is equal to 2. Okay. Now, we take K is equal to 2. K is equal to 2. And that is k less than or equal to rank of A. Less than or equal to is there. Therefore, k is equal to 2 is equal to the rank of A. So, this condition is also satisfied. So, now the set consisting of I, A, etc. a power k, k is 2. The set consisting of I, a power k means a square. Spans means take the linear span. And that will be equal to the linear span of I, A only. Why? Because A square is A. Because A square is A, you can see. You can check. Take A, square it, it is A. So what happened? The dimension of I, A square is equal to the dimension of I, A is equal to 2. Is equal to 2. Right, and 2 which is not equal to k plus 1. Is it spanning k plus 1 dimensional subspace? Where k is 2 means k plus 1 means, is it spanning 3 dimensional subspace? No, it is spanning only 2 dimensional subspace. Right, that is why this option 2 is not true. Option 2 is not true. So, summarizing all the options, the true options are, and the answer to this question is options 3 and 4. That is the detailed discussion of this question from the section Linear Algebra, which is related to the concepts and the results related to spanning sets and linearly independent sets. And it is a very simple, straightforward question. Even such kind of problems, even a BSc student can very easily do it. Right. It is very simple, and it is based on very simple concepts. I am sure that you have understood the solution of this problem. Thank you for watching this video. Now, please like my videos and share them with your friends and colleagues. Please join in my channel as a member and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure we'll be meeting all of you again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.